Hi, this is Schwartz from MasterMathMentor.com. This is video BC21. Topic is alternating series, and it covers the BC manual pages 107 and 108. Consider the infinite series, summation n equals 0 to infinity, of 1/3 to the n power. This is a geometric series whose terms are 1 plus 1/3 plus 1/9 plus 1/27 plus 1 over 81. And because r is less than 1, this is a convergent series. Now consider the series summation n equals 0 to infinity of negative 1/3 to the n. This is also a geometric series, and it is convergent because the absolute value of r is less than 1. However, the terms are now 1 minus 1/3 plus 1/9 minus 1/27 plus 1 over 81 minus ... Because the terms switch sign, we call this an alternating series. Alternating series generally have a telltale sign, and within the series there's usually a negative 1 to the n power or negative 1 to the n plus 1 power. If we look at summation n equals 1 to infinity of negative 1 to the n, a sub n, that is equal to negative a sub 1 plus a sub 2 minus a sub 3 plus a sub 4 minus ... However, if we look at summation n equals 1 to infinity of negative 1 to the n plus 1 power of a sub n, then we have a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus ... So with negative 1 to the n, the odd terms are negative. With negative 1 to the n plus 1, the even terms are negative. However, sometimes the series is summation n equals 0 to infinity of negative ... 1 to the n, a sub n. And now the terms are a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus ... And if our series is summation n equals 0 to infinity of negative 1 to the n plus 1, a sub n, then we get negative a sub 1 plus a sub 2 minus a sub 3 plus a sub 4 plus minus ... So when we start at n equals 0, negative 1 to the n will have the even terms being negative, and when we start at n equals 0, we have a negative 1 to the n plus 1, the odd terms are negative. The test for convergence for an alternating series is probably one of the easiest. There are two conditions. First, limit as n approaches infinity of a sub n has to equal 0. This is our nth term test, which our series and all series must pass in order to be convergent. Secondly, a sub n plus 1 must be less than a sub n for all n greater than some value of capital N. What this says is that the absolute value of the terms must eventually decrease. The terms must eventually be getting smaller. So the 7th term is less than the 6th term, the 8th term is less than the 7th term, etc. In number 1, we're asked to find the possible convergence or divergence of the series negative 1 plus a half minus a third plus a fourth minus a fifth plus ... This is the alternating harmonic series. We first write our series using sigma notation. Summation n equals 1 to infinity of negative 1 to the n times 1 over n. And now we apply our alternating series test. First, the nth term test. The limit as n approaches infinity of 1 over n is certainly equal to 0. And next, the terms do decrease. 1/4 is greater than 1/5. 1/5 is greater than 1/6. So 1 over n is greater than 1 over n plus 1. And that means that the series converges. Although not necessary, we graph the first 6 points and join them with lines just to make it easier to see. It should be clear that the limit as n approaches infinity of our expression is equal to 0, as the curve is alternating, going below the axis, then above, then below, then above, but getting closer and closer to the x-axis. And obviously the terms are decreasing in value as well. Notice also that we say the series converges, but we have no idea what it converges to. Later in the course, we will show that this actually does converge to negative natural log of 2. Number 2 is different as the problem is given in sigma notation form. Sigma n equals 1 to infinity of negative 1 to the n plus 1 times n over 2n minus 1. And again, we would like to show whether this is convergent or divergent. We first write out our series term by term. 1 minus 2/3 plus 3/5 minus 4/7 plus dot dot dot. This is clearly an alternating series. So we apply our alternating series test, starting with the nth term test, and look at the limit as n approaches infinity of n over 2n minus 1, and we get 1/2. This is not equal to 0, so right away we know the series diverges and we can stop. If we were interested, though, in whether the terms were getting smaller, we'd have to check whether n over 2n minus 1 is greater than n plus 1 over 2n plus 1. In order to do that, we will get a common denominator and determine that 2n squared plus n over 2n minus 1 times 2n plus 1 is greater than 2n squared plus n minus 1 over 2n minus 1, 2n plus 1. The denominators are the same, but the left side numerator is bigger than the right side numerator. So the terms, yes, are getting smaller, but the series is still divergent. The graph confirms our result. We see the points on either side of the axis, so the points show an alternating series. And as you go further on, they are about the same distance from the x-axis. So it's like adding a half and then subtracting a half, and adding a half and subtracting a half. This will not converge because we expect it for convergence to get closer to a number. And this will oscillate between a bigger number and a smaller number. So this is definitely divergent. In problems 3 through 5, you are given 3 alternating series, and your job is to show that each one is divergent. 3 reads summation n equals 1 to infinity of negative 1 to the n plus 1 times n plus 2 over n. When we write this series out, we get 3 minus 4 over 2 plus 5 over 3 minus 6 over 4 plus dot dot dot. The limit as n approaches infinity of n plus 2 over n is equal to 1, and therefore this fails the nth term test. When we see the graph of our points, it is clear that we will be eventually adding number close to 1 and subtracting a number close to 1, then adding and subtracting, and therefore our sum does not settle down to a number. This is divergent. Number 4 reads summation n equals 1 to infinity of negative 1 to the n plus 1 times the square root of n over the cube root of n. We won't write the series here, but it's clear because of the negative 1 to the n plus 1 that it is alternating. When we look at n, the square root of n over the cube root of n, we can write that as n to the 1/6. So our series is summation n equals 1 to infinity of negative 1 to the n plus 1 times n to the 1/6 power. And the limit of that expression is equal to infinity. Therefore, this fails the nth term test and is divergent. It is clear by looking at the graph that the points are getting further from the x-axis, and there is no way that this can converge. 5 reads 4 over 1 minus 2 over 1 plus 4 over 2 minus 2 over 2 plus 4 over 3 minus 2 over 3 plus dot dot dot. This is the only challenging problem here. It is alternating, but it is not quite clear whether the terms are getting smaller. We see this in the graph. 4 is bigger than 2, but then the second and third terms are both 2. The fourth term is 1, but then the next term goes up to 4/3. So unless we can write this as a sigma notation problem, it's going to be very difficult to apply the alternating series test here. This is where we get a little bit clever though. If we rearrange our terms, putting all the positive terms first and then all the negative terms, we have 4 over 1 plus 4 over 2 plus 4 over 3 plus dot 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 minus 2 over 1 minus 2 over 2 minus 2 over 3 minus dot dot dot. And this can be written as summation n equals 1 to infinity of 4 over n minus summation n equals 1 to infinity of 2 over n, which is equal to summation n equals 1 to infinity of 2 over n. This is a divergent series because it is the harmonic series. So the expression is divergent. Back when we studied Taylor polynomials, we examined errors in using those Taylor polynomials using the Lagrange remainder. That method of finding errors worked fairly well, but was a bit cumbersome when all the terms of the series was positive. But when they alternate, things are decidedly easier. Since the terms of the series gets progressively smaller, then the error in approximating the value of an alternating series using n terms is simply the absolute value of the n plus first term. Let's see this rule in action. We would like to find the range of the sum of the series summation n equals 1 to infinity of negative 1 to the n plus first power over n factorial using its first 5 terms. We first write out the series summation n equals 1 to infinity of negative 1 to the n plus 1 over n factorial, and we get 1 minus a half plus 1/6 minus 1/24 plus 1/20. And that is a convergent alternating series, as the terms are getting smaller and the limit of that expression is 0. Now, if we look at summation n equals 1 to 5 of negative 1 to the n plus 1 over n factorial, we get 1 minus a half plus a 6 minus 1/24 plus 1 over 120, which is equal to 0.633 bar. So the error in using 5 terms will be the absolute value of the 6th term, which is the absolute value of negative 1 over 6 factorial. Therefore, we can say that summation n equals 1 to infinity of negative 1 to the n plus 1 over n factorial has to be between 0.6319444 and 0.633 bar. Let's show this graphically. We first show in blue the sequence a sub n equals negative 1 to the n plus 1 over n factorial. We use lines to make it a little bit clearer, but we can see the points, and we can see that this is certainly alternating, as they are first positive, then negative, and positive, and negative, and they get smaller and smaller. The red represents the summation n equals 1 to infinity of negative 1 to the n plus 1 over n factorial. And notice how after a few terms, it is starting to level out. So let's now look at a few more terms and zoom into these points. We first look at 5 terms, summation n equals 1 to 5 of negative 1 to the n plus 1 over n factorial. And in green, we see the dot at 0.63333. We then add on the next term, which is negative 1 over 6 factorial, and we get 0.63194. Now, since the series is alternating, the next term will go up and then go back down. So the true value of summation n equals 1 to infinity of negative 1 to the n plus 1 over n factorial must be between 0.63194 and 0.63333. Therefore, the maximum error is 1 over 6 factorial. Sometimes a series may have both positive and negative terms, but may not be an alternating series. For instance, the series summation n equals 1 to infinity of cosine n over n cubed is equal to cosine 1 plus cosine 2 over 8 plus cosine 3 over 27 plus cosine 4 over 64 plus dot dot dot. This has both positive and negative terms, but they do not alternate, as you can see on the graph. It almost appears that the terms are random in terms of sign. How do we determine whether this series converges or not? Here is the procedure. We will first look at summation n equals 1 to infinity of the absolute value of cosine n over n cubed. This is the absolute value of cosine of 1 plus the absolute value of cosine 2 over 8 plus the absolute value of cosine 3 over 27 plus the absolute value of cosine 4 over 64 plus dot dot dot. And we will also compare this to summation n equals 1 to infinity of 1 over n cubed, which is 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus dot dot dot. This is a convergent p-series. By the direct comparison test, cosine of n will always be less than 1 for any value of n. Therefore, the summation n equals 1 to infinity of the absolute value of cosine n over n cubed must be less than summation n equals 1 to infinity of 1 over n cubed, and therefore must be convergent as well. And since summation n equals 1 to infinity of cosine n over n cubed, which contains both positive and negative terms, has to be less than the summation n equals 1 to infinity of the absolute value of cosine n over n cubed, which only contains positive terms, then summation n equals 1 to infinity of cosine n over n cubed must be convergent as well. This problem can be summed up by a general rule and several new definitions. If summation of the absolute value of a sub n converges, then the summation of a sub n must converge as well. So a series that has what we call absolute convergence has both summation of the absolute value of a sub n and summation of a sub n converging. But a series that has conditional convergence has summation of a sub n converging, but the summation of the absolute value of a sub n diverging. On number 5, A through C, we are to show work to determine whether these series converge conditionally, converge absolutely, or diverge. A reads summation n equals 0 to infinity of negative 1 to the n times n squared over n plus 1 quantity squared. To do this, it's always a good idea to write out the first few terms of the series, and we get 0 minus a quarter plus 4/9 minus 9/16 plus ... It certainly is alternating. We start with the nth term test and look at the limit as n approaches infinity of n squared over n plus 1 quantity squared, and this is 1, which is not 0. So this is a divergent series and nothing more need be done. Number 5b reads summation n equals 0 to infinity of negative 1 to the n times 8 over the square root of n plus 1. We write out the first few terms and we get 8 minus 8 over the square root of 2 plus 8 over the square root of 3 minus 8 over the square root of 4 plus ... This certainly passes the nth term test, as the limit of 8 over the square root of n plus 1 as n approaches infinity is equal to 0. And the terms definitely decrease. So the series itself is convergent. We then take a look at summation n equals 0 to infinity of the absolute value of negative 1 to the n over 8 over the square root of n plus 1. And because of the square root in the denominator, this is a divergent p-series. So while the original series that is alternating is convergent, the series with absolute values, making all the terms positive, is divergent. Therefore, summation n equals 0 to infinity of negative 1 to the n times 8 over the square root of n plus 1 is conditionally convergent. C reads summation n equals 1 to infinity of negative 1 raised to the n squared plus n over 2, all over 2 to the n. Here's an example where writing out the series will really help us to see what's going on. This is negative 1/2 minus 1/4 plus 1/8 plus 1/16 plus ... We realize, though, that summation n equals 1 to infinity of the absolute value of negative 1 to the n squared plus n over 2, all over 2 to the n, is the same thing as summation n equals 1 to infinity of 1 over 2 to the n. And we know that summation n equals 1 to infinity of 1 over 2 to the n is a convergent geometric series. So if that series converges, the original series with its some terms negative, some terms positive, would also have to converge. And therefore our original series, summation n equals 1 to infinity of negative 1 raised to the n squared plus n all over 2 to the n, is absolutely convergent. Finally, looking at the series summation n equals 1 to infinity of negative 1 to the n plus 1 over n, we get a result that cannot possibly be true. Let's see if we can find the fallacy. We start by calling this series S. It is an alternating harmonic series, and we show a bunch of terms. 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, plus a seventh. And we show some more terms, plus ... Now let's double each side. And we end up with 2s equals 2 minus 1 plus 2/3 minus a half plus 2/5 minus a third plus 2/7 minus a fourth. And again, we show some more terms, plus ... Now let's do some rearranging of terms. We have 2s is equal to 2 minus 1. we'll bring the negative 1/2 as our next term, and then a 2/3 and a negative 2/3, then a negative 1/4, and then a 2/5 minus 1/5, and etc. And now we will combine the terms with the same denominator. So we get 2s is equal to 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 plus dot dot dot. But what is that series? That series is what we started with, s. So we have 2s is equal to s, and therefore 2 is equal to 1. Obviously, there's something wrong. But what is it? The theory is well beyond the scope of this course, but our issue is the act of moving terms around in an infinite series. By doing that, you can actually change the value of the series. As we mentioned many times before, as soon as you mess around with infinity, you can get yourself into a lot of trouble.